Today we're going to talk about function characteristics, including a review of intercepts, zeros, domain, and range, as well as our new concepts, continuity and end behavior. For function families, we just finished our unit on absolute value, where the parent function is y equals the absolute value of x, and looks like a V shape as shown here on the left. Our next unit will be quadratics, and in quadratics, our parent function is y equals x squared, and it's our parabola here that we worked with quite a bit in Algebra 1, but we're going to go a little more in depth here in Algebra 2. So these two types of functions are going to be most of the ones we'll look at today. First, let's review our x and y intercepts. An x-intercept is the point where the graph crosses the x-axis. Here, if you look at this graph, it crosses the x-axis at -5, 0, at -2, 0, and again at 3, 0. These 3 points would be our x-intercepts for this particular function. The y-intercept is the point where the graph crosses the y-axis. And if we look on our graph here, it crosses the y-axis only once at 0, 4. That would be our only y-intercept for this function. Let's review our zeros. A zero of a function is the x value at the x-intercept. It can also be called a root. So our zeros are the functions shown on the right. We're going to look first for the x-intercepts at -1, 0, and at 3, 0. So these x values, -1 and 3, would be our zeros. Next, let's look at domain and range. The domain is the set of x values in a relation. We learned last week that in absolute value, the domain is always all real numbers. But if we don't remember that, we can always look to the left and look to the right and look at what our x values can be. I usually start at the vertex. So if I go to the left, x keeps going. We see that arrow on the end, it's going to continue. If we look to the right, x still keeps going. So x can be all real numbers, or we could also write it as -infinity to +infinity in our interval notation. Our range is the set of y values in a relation. Here, we're going to start at our vertex, which is at -2, 4. And I'm going to look specifically to my y value here. My y value in the vertex is 4. So for my range, I can write out that y, and I'm going to leave a space, and I'm going to put 4. And from here, I look at the vertex and see what direction I'm going. So from the vertex, this function goes down. So the y values can be anything less than 4. But it can also be equal to 4, so I write less than or equal to in between y and 4. In my interval notation, I do my smallest value to my highest value, and my smallest value, well, y keeps on going down to -infinity. So -infinity will be first, and 4 will be second. Next, our first new concept, continuity. This one is much easier than it sounds. A continuous function means the function is a single, unbroken curve. If you trace it with your pencil, and you don't have to pick it up, it is continuous. So if we look at this graph here on the left, if I trace that with my pencil, I would never have to pick my pencil up. It is continuous. Discontinuous means the function has breaks in its curve. And we do the pencil test again. Trace it with your pencil. If you have to pick it up, it's discontinuous. With this function on the right, if I trace here, you notice when I get to this point, I have to pick up my pencil to go up here. So when I have to pick up my pencil, that means it is discontinuous. Now, on to end behavior. The end behavior is exactly what it sounds like. It is what happens to the function on either end. So it describes what happens to f of x as x gets very small, -infinity, or very large, +infinity. Which essentially means as the graph goes left, where does y go? So if we look to this side, as it goes left, y goes up. So y is going towards positive infinity. Then, as the graph goes right, as x goes towards positive infinity, because that's what's over here on the right, as we go to the right, y goes up. It is going up towards positive infinity. So we would write the end behavior like this. And I always usually write it out and I leave a blank beside f of x. Remember, f of x is the same thing as y. So as x goes to, that arrow means goes to, as x goes to negative infinity, the function goes to, and we fill in our blank here. And it went up towards positive infinity, so that's what we put. We have a second part of this. So we talked about the left, now we have to talk about the right side. As x goes to positive infinity, the function f of x goes to, and it was also going up to positive infinity. Let's practice with an example. Here we have the graph of a quadratic function. So first we're going to list our x-intercepts. And if I look here, it crosses the x-axis at negative 3, 0, and 1, 0. So my x-intercepts are those 2 points, negative 3, 0, and 1, 0. My y-intercept is where it crosses the y-axis, here at 0, 2. My zeros, I'm just going to look at these x-intercepts at negative 3 and 1. That's our x values of our x-intercepts. So that's what I put here for my zeros. Next, our domain. Very similarly to absolute value, our quadratics have a domain of all real numbers. If you look, whether their quadratic is pointed up or down, as we go to the left, it keeps going. As we go to the right, it keeps going. So our domain is going to be, once again, all real numbers. So as we look across here, it keeps going both directions. So I would write my interval notation, negative infinity, comma, positive infinity. Our range, just like with absolute value, we start at the vertex, because if you notice, that's our highest point right here. Y doesn't get above that vertex. So we start there. And that point is at negative 1, 3. Once again, it's range. I'm looking at my y value, which is 3. So I can write y and 3. But then over here, I see that we go down from that point. So my range, my lowest value is negative infinity, because it keeps going down forever. My highest value is positive 3. So my range would be negative infinity to positive 3. To find out if it's continuous, I use the pencil test. I trace along the function. And we go up, and we trace it back down. But I didn't have to pick up my pencil, so yes, it is continuous. For our end behavior, we look first to the left side, and then to the right. And I can write out my end behavior as x goes to negative infinity, f of x goes to, and leave a blank. As x goes to positive infinity, f of x goes to blank. And then just fill these in. So as we go to the left, it goes down towards negative infinity. So I can fill that in here. As we go to the right, we're going down forever towards negative infinity. So that is also what I would fill in here. Okay, that's all for our video today. Let's practice a little bit.